Check it out now, y'all.
NanoHub U, online instruction.
If you recall the last lecture, we discussed the details of the Michelson-Morley experiment, and we came to the conclusion that based on the experimental data, the speed of light is a constant independent of the direction in which it propagates. And this, of course, caused a big issue because according to the Galilean transformation of velocities, you would expect the speed of light to shift by the velocity of a reference frame, depending on where the speed of light was measured, which reference frame it was measured from. So this experimental fact that the speed of light is constant caused the development of what are now referred to as the Lorentz-Einstein Transformation equations. These are equations that replace the Galilean transformation equations and allow you to go from a moving frame to a fixed frame in such a way that the speed of light remains constant, independent of the velocity of the moving reference frame. Technically, I could just present the final equations that Lorentz-Einstein have derived, but it's kind of useful, I think, to try to provide an overview, try to remind you where we have been for the last 3 lectures, and perhaps give you a clearer understanding of why these Lorentz-Einstein transformation equations are so important in the way we think about modern physics. So what I'd like to do is I'd like to try to recap the previous 3 lectures. We discussed many separate topics in somewhat of a disjointed way. I'd like to make an attempt to provide a continuous narrative that summarizes a lot of the important themes that permeated these previous lectures. So, in terms of the major theme, right? The major theme is we'd like to make sure that the laws of motion that we discover here on Earth are universal, that they apply anywhere within the universe. I mean, if the laws of motion that we're dealing with don't apply everywhere in the universe, then what's the point? It's like who are we trying to kid? And so one way to address this question is to figure out when these laws of motion that have been developed by Newton, when they might break down. So that's the major theme. It's a very noble idea because you want to try to find out the range of validity of these physical laws that we put so much stock in when we're here on Earth. Now, that major theme has a variety of sub-themes, right? And the sub-themes are that for about 200 years, Newton's laws of motion were thought to be valid in any inertial reference frame. So if you wanted to go to another part of the universe, as long as that part of the universe was in constant velocity with respect to, let's say, the Earth, then you could expect Newton's laws to apply there. How would you take measurements from one reference frame that's moving at a constant velocity v sub f and translate those measurements back to, let's say, a stationary reference frame? Well, you would have to use the Galilean transformation to jump between these reference frames. Now, in around 1865, the laws of electricity and magnetism were finally synthesized in the form of Maxwell's 4 equations. And basically, I mean, this isn't entirely true, but basically, the idea was that if you have a charge that's static, that charge is going to produce electric fields. And if you have a charge that's moving, in other words, you have a current, that current is going to produce magnetic fields. And the feeling was that the electric field and the magnetic fields were completely different phenomena. They were just 2 separate topics in a branch of physics called electricity and magnetism. Now, Maxwell changed that when he made a startling prediction, right? He predicted that something called an electromagnetic wave could exist, and this electromagnetic wave would move with the speed of light, which is referred to as c. Now, based on the Galilean transform that's been around for something like 200 years, you would expect the velocity of light to depend on the inertial reference frame from which it is measured. So in other words, if you're moving away from a beam of light at a velocity v sub f, you would expect the speed of light to decrease by the velocity that you're moving away from that light beam. Conversely, if you're moving toward a light beam with a velocity v sub f, right, you would expect that the velocity of the light beam would increase by the speed of the reference frame. The trouble was, when you looked at Maxwell's equations, he predicted a universal value for the speed of light c, and there was no mention of any inertial frame of reference. And so how do you reconcile this idea that there's no reference frame to predict a standard value of c with the fact that the velocity of light should depend on the motion of the reference frame from which you make the measurement? Well, if that was the only problem, maybe it wouldn't be so serious of an issue, but several thought experiments involving electricity and magnetism eventually predicted results that seemed to depend on the velocity of the inertial reference frame. So you got different answers depending on what reference frame you made a measurement, right? So this was very problematic and puzzling, and if you go back and look at lecture 12.02, I actually worked through one example where I tried to show that depending on what reference frame you were in, the force between two charges could be different. So to solve these issues, right, this concept of the ether was introduced, and the claim was made that Maxwell's equations as derived must be valid in a special frame of reference in which the ether is stationary. So that was the state of the understanding up until, let's say, 1870. And at that point in time, Michelson and then later Michelson-Morley decided to take advantage of the Earth's velocity around the sun to measure the speed of light in different directions. And their thought was that once and for all, they were going to determine the Earth's motion with respect to the ether, and in that way, they would define the reference frame in which Maxwell's equations are thought to be valid. Well, the upshot of Michelson-Morley's experiments, they constructed this very elaborate interferometer, very clever idea, right? The upshot of their measurements was that the velocity of light, or the speed of light, was constant in all the inertial reference frames. It didn't matter what direction the light beam was moving in. You constantly got, you always achieved the same velocity. You always measured the same speed for that light beam. So that was a real puzzle, right? And then historically, the question becomes, what do you do next, right? How do you sort this out? Well, there were basically two approaches, right? A number of prominent physicists at the time decided to keep this ether concept, and what they did is they cooked up some ad hoc transformations to explain the Michelson-Morley experiment. Now, these cooked up explanations required transformations, but ultimately people believe these transformations were just a math trick to manipulate Maxwell's equations so that you could explain the results of the Michelson-Morley experiment. They didn't believe there was anything fundamental in these transformations. They were just tricks. Einstein, on the other hand, in 1905, took a completely different point of view. What he decided to do was he decided to focus on electromagnetic fields. And he immediately abandoned the ether concept, and he focused on Faraday's law of induction. And he insisted on faith that Faraday's results should be frame invariant. So you might recall what Faraday's law of induction is. It just says if you take a wire and you form a simple closed loop, and then you take a magnet, right? And if you push the magnet through the wire, right, you will induce a current in the wire, and the direction of the current depends on the direction of the motion of the magnet with respect to the wire. It's even more interesting than that because you can hold the magnet fixed and move the wire, and you're going to get exactly the same result. This was something that Faraday discovered in 1831. The reason Faraday's law was so interesting is because it embodied this principle that magnetism and electricity were somehow connected, right? That you could take magnetism and you could convert it into electricity. So Einstein argued that if the laws of electricity and magnitude do not depend on the frame of reference, in other words, they are the laws of electricity and magnetism are frame invariant, then he argued that the speed of light c at which these magnetic fields propagate. So when you move the magnet with respect to the loop, you're changing the magnetic field through the loop. That magnetic field has to propagate, and it's going to propagate at the speed of light. And since the results of the experiment just depend on the relative motion of the magnet to the loop, he said, well, the speed of light has to be constant, right, for all observers. And so this actually agreed with Michelson-Morley's experiment, right? And so just by insisting that this law of electromagnetic fields that was discovered by Faraday, just by insisting that that be frame invariant, he also comes to the conclusion that the speed of light has to be constant, independent of the reference frame from which it's measured. He also looked at the situation in a bit more detail, and I try to sketch it out here in two diagrams, right? It's a little bit complicated, but it's worth trying to talk through the argument so you can at least appreciate it. In the first argument, we have a reference frame that's moving, and that reference frame is attached to the loop. And we move the loop toward the magnet, and we ask what causes the induced current in the loop. Well, the answer to that question is there are electrons in the loop. Those electrons acquire a velocity, v sub f, right? There's a component of the magnetic field acting on the electrons in the loop. That component of the magnetic field that's perpendicular to the velocity of the loop produces a Lorentz force, which is this QV cross B force. And this QV cross B force causes electrons to circulate around the loop and produces the induced current that we all know from Faraday's law of induction. So it's important to realize that in this frame of reference, there's no E field that drives the current through the loop. The only field that's present is the magnetic field from the magnet. Now, Einstein said, well, you should be able to discuss the problem in a different frame of reference, and that different frame of reference, S prime, could be attached to the magnet. So now this frame of reference, S prime, which used to be associated with the loop, is now attached to the magnet. The loop is held fixed, the magnet is moved, right? And we ask the question, what happens in this situation? Well, because the loop is fixed, the electrons in the loop essentially have no velocity. So if the electrons in the loop are at rest, their velocity is zero, and that implies that this QV cross B force, which drove the current through the loop in this situation, that implies that this force is going to go to zero, right? If you go back and you recall Maxwell's laws for electricity and magnetism, there's one law that says a changing B field produces a circular electric field. And in this frame of reference, it's this circular electric field that acts on this loop of wire that drives the current through the wire. So in this frame of reference, there are two fields, right? One field is a magnetic field produced by the magnet. The second is a circular E field, right? And so there's a discrepancy between these two situations. In one case, you just have a magnetic field. In the other case, you have both an electric and a magnetic field that produce the current. And of course, the current that flows, right, is the same in both cases. So that's a fundamental problem, right? That's a fundamental problem. And basically, it says that depending on what reference frame you're in, you see different electric and magnetic fields. And the question is, how can this be? And what Einstein concluded was that the electromagnetic field responsible for the current flow is just different depending on which reference frame you're in, right? So depending on where you're observing the experiment, you're going to get different values for the electric and magnetic field. So Einstein argues, well, if this happens to electromagnetic fields, if the values of the electromagnetic fields depend on the frame that they're observed in, then maybe the same thing happens when you think about how space and time are coupled together, right? So this idea that electric and magnetic fields can appear differently to different observers was then applied to the concept of space and time. Einstein derived similar transformation equations to describe how space and time are coupled. These transformation equations that Einstein derived are exactly the same as those of Lorentz, hence they're referred to as the Lorentz-Einstein Transformation equation. And in contrast to other people, right, Einstein realized that this coupling of space and time led to a new theory, which is now called special relativity, and this theory of special relativity changes the way we think about the world. Literally, it literally forces us to reevaluate many things. So in a few minutes, about 15 minutes, that's kind of a big discussion or a quick discussion of the overall framework, the logic that takes you from Galilean frames of reference all the way up to Lorentz-Einstein transformation equations. And what I'm going to do in the remainder of this lecture is I'm going to write down these transformation equations. We're just going to derive those in a very simple way. And then we're going to devote the next week or so to trying to learn how to use those equations to describe events in different reference frames. So Einstein's approach tangles space and time. It can be confusing, and it needs very careful definitions. And I think the primary insight is that when you try to define what space and time is, you have to realize that you have to resort back to experimental data. And so if you ask the question, what is space? Space is going to be what you can measure with a measuring rod. And if you ask the question, what is time? The answer to that question is time is what we measure with a clock. And any other concepts of space and time that do not fall into this definition are not well defined. That's the argument. So it's important to realize that all the discussions we're going to have in the next week or so are going to ultimately come back to measuring locations with a measuring stick and measuring time intervals with some sort of a clock, right? And if you don't understand that, you'll find that our discussion is going to be somewhat confusing. It turns out there are many ways to derive these Lorentz-Einstein transformations. Perhaps the most elegant way is to write out the coordinates and the time in the prime system and connect those to the coordinates and time in the unprimed system using a 4x4 matrix, where in principle ahead of time we know nothing about the elements of this matrix. It turns out by very elegant mathematical arguments and by using various symmetry constraints, you can actually write down expressions for each of these 16 elements in this Lorentz-Einstein transformation. That takes about 20 or 30 pages of algebra plus argument, and we're not going to follow that approach here. It's not very practical to lecture about that. There are other ways to derive the values for these different elements in this transformation matrix. And what I'm going to do in this lecture is I'm going to try to apply some physical intuition and give you some insight into how you might derive this transformation. The derivation is not going to be as mathematically rigorous as for instance, it would be if we followed the first approach. But nonetheless, the answers we get do match up with the more rigorous approach, and it's a little bit easier to comprehend and understand. So I'm going to try to use some physical intuition to justify the Lorentz-Einstein transformation equation. So I'm going to start off by reminding you what the Galilean transforms are between the primed and the unprimed inertial reference frames. And I'm going to point out that there's an inherent problem in these transformation equations, and that problem is that the location in space and the position and the location in time are asymmetric, right? There's a different equation, different form of the equation that describes the spatial coordinate, and a different form of the equation that describes the time coordinate. And so we're going to speculate that perhaps a better transformation equation is going to result if we can make the transformation in space and time more symmetric. And we do that by adding a term to the time equation, and then by multiplying both equations by some constant gamma. So the argument is this now treats space and time in a more symmetric fashion than the Galilean transform. And of course, our challenge is going to be to somehow figure out what the value of alpha is and what the value of gamma is to satisfy two constraints. One constraint is that the speed of light is going to be constant in both reference frames, and then we're going to have to cook up a second constraint to allow us to get an expression for gamma. So how do we get alpha? Well, we get alpha by taking differentials of these two equations, and then we divide those two differentials one by the other to get velocities. So dividing dx by dt, we get an expression that looks like this. dx by dt is just going to be the velocity u of an object that we measure from a stationary reference frame. We're going to define the velocity of that object in the moving reference frame as dx prime dt prime, and we're going to call that equal to u prime, right? And the velocity of our reference frame is, of course, given by v sub f. So if you just follow through the arithmetic, using this proposed form of the transformation equations between x and x prime and t prime, what you find is you find an expression that looks like this. And now what we're going to insist on is we're going to insist that if u prime is equal to c, so that if we measure a beam of light in the moving reference frame, and that beam of light is moving at the speed of light c, then we're also going to measure the same speed c in the stationary reference frame. So that's the primary result of Michelson-Morley's experiment. So we want to choose a value of alpha such that if u prime is equal to c, u is also equal to c. Well, it's simple to work out. This is the equation. You put u equal to c, you get here. You put u prime equal to c, you get this. You solve this expression for alpha, and what you find out is that alpha has to be v sub f over c squared. And so this then gives the velocity transformation equation, and it gives an expression for alpha. And this transformation equation has some interesting characteristics. In particular, if the velocity of the moving reference frame is much, much smaller than the velocity of light c, then this transformation equation reduces back to what you would expect. the Galilean transformation equation that had been used for something like 200 years. So as long as the speed of an inertial reference frame is very small compared to the speed of light, the velocity transform equation reduces back to what had been used by Galileo and all of his disciples. So that gets rid of alpha. That gives us an expression for alpha. What do we do about gamma? Well, to get gamma out, we're going to need some other constraint, some other equation. And I'd like to remind you the importance of invariants when you transform reference frames. And I do that with this simple analysis, which you're probably all familiar with. If you got a point P located in space, and that point P is located in a coordinate system which is designated by X and Y, and then I rotate that coordinate system, X and Y, to form a new coordinate system, X prime and Y prime. And of course, that new coordinate system is rotated by an angle theta with respect to the old coordinate system. Then, if I measure the coordinates of this point P in the X prime, Y prime coordinate system, I'm going to get a coordinate X0 prime and a coordinate Y0 prime, right? And the question then becomes, how are the initial coordinates X0 and Y0 of the point P related to the coordinates X0 prime and Y0 prime in the rotated coordinate system? Well, I sketch out the geometry that allows you to derive that transformation equation. These are the equations that you've probably seen in many textbooks. And the interesting point of this discussion is that the distance that this point P is from the origin, that distance S, has got to be independent of the coordinate system, be it X or Y or X prime and Y prime. And the reason is the point doesn't move, it's just the coordinate system that does. And so this separation distance of P from the origin has got to be an invariant. And that just simply means that the X0 squared plus Y0 squared, those are the coordinates in the unprimed coordinate system, have to be equal to X0 prime squared plus Y0 prime squared, which are the coordinates in the prime coordinate system. And if you use this transformation, you can show this quantity, this equation is true. And that just simply means that the distance squared is an invariant for this particular type of transformation. So we want to take that insight and apply it to our discussion about how light moves in space. And we want to ask, is there an equivalent invariant in space-time? And the answer is there is. What you have to do is you have to think about how light moves along the x direction. And so, for instance, it's useful to plot the distance x that light travels in a time interval t. Right? If you take that time interval t that the light travels and multiply it by the speed of light, then you're going to get the distance x that the light beam moves. And so the motion of the light beam along a positive x direction, right, is going to be just given by this red line. There's an equivalent line which is indicated by the blue line, and that tells how light moves in the minus x direction. And so we've got two equations that describe how light propagates either along the plus x or the minus x direction. The question is there a single equation that tells how light moves along the x-axis? And the answer is that these two equations can be recovered from this equation, which is quadratic. Because it's quadratic, it has a positive and a negative root, and those two roots of opposite sign match the two cases that we've already discussed. And so this equation here describes how light moves in the x direction, and this equation can be rewritten in this form. And of course, it's equal to 0. And so the suggestion is that because it's equal to 0, there should be an equivalent equation in a moving reference frame that describes how light propagates in the moving reference frame. Of course, light is going to propagate at the same speed c, in that moving reference frame. And so the thought is that since this equation basically describes how light moves, this quantity should be an invariant between the two reference frames. And so what we do is we just set these two expressions for how light propagates in the stationary and in the moving reference frame. We set those equal to each other because we like to believe that's an invariant quantity. So the remainder of these slides just go about following the consequences of that identification. What we do is we take the S invariant, which is given by equation 1, we set it to the same invariant in the frame S prime, which we call equation 2. We have a proposed transformation between the unprimed and the prime coordinate system, which is here. We've already got an expression for alpha. So we're just setting up this equation here, and we're asking what value of gamma is required in order to make this equation true. You can follow through the arithmetic, and what you find at the end of this derivation, several terms cancel out. But what you find at the end of the derivation is that this quantity gamma has to be equal to square root of 1 minus v sub f squared over c squared, right? And this quantity then makes this expression for how light propagates in a coordinate system invariant, independent of the motion of that coordinate system. So this quantity gamma is defined in that way. This derivation is not rigorous, but it does give the right answer. And it leads us to a final summary slide, which allows us to identify the Lorentz-Einstein transformation equations in terms of this parameter gamma, which is defined over here, right? And also gives rise to the velocity transformation equation. So these equations are very interesting because they accomplish two facts, right? One fact is they make this quantity invariant, independent of the motion of a reference frame. And the second thing they accomplish is they give you a constant value for c, independent of the velocity of the moving reference frame v sub f. Okay? So the remainder of the discussion about relativity, about special relativity, is actually going to be learning how to apply these equations to describe different events in different reference frames. And so the next lecture, which will be shorter than this one, we're actually going to talk about relativistic time and distance intervals. And we're going to show you how to use these equations in order to analyze events that occur in different reference frames that are in motion with respect to a stationary frame. So come on back and listen to that. It's going to be kind of interesting. The results are counterintuitive, and they will show you, right? They will show you firsthand how space and time are mixed up because they appear somewhat symmetrically in this Lorentz-Einstein transformation. So thanks for listening to this, and we'll see you at the next lecture.